In the previous video, we dealt with kinetic theory of gases and how the atomic hypothesis and understanding of energy connects to temperature. We're going to go back now and have a little bit of a discussion of an earlier time. Heat was originally thought about in the early 1800s and in the 1700s, long before the atomic hypothesis. It was thought to be a fluid. It was called caloric. And the reason they thought of it as fluid because they noticed that the temperature tended to flow. It seemed like heat was flowing from the hot side to the cold. Now, today we know that there is no substance flowing. It's the energy flow due to the temperature difference that we call heat. And that heat is just the flow of energy, and it's no different than any other type of energy. But this was not so obvious to anybody. James Prescott Joule gets generally the credit for what is known as the law of the conservation of energy. And what he did was he showed that mechanical energy and heat energy were one and the same, that there was no difference. And the idea of his thing can be shown kind of like this. If you have some sort of container and you have a thermometer shown in green, and you were to close your eyes and I heated the water or whatever's in this container, then I could raise its temperature to some value. Maybe I raised that temperature to 80 degrees C. And I did that by heating. But if you had closed your eyes, I could have raised the temperature to 80 degrees C also by providing energy in the form of mechanical work. Now we know that that makes total sense because what the temperature is measuring is the internal energy per molecule. And so how that energy gets deposited, whether it comes from the form of heat transferring the energy due to a temperature difference or by energy put in by some other means, such as by doing work on the system, we don't know. All we know is that energy got in, and that's what the 80 degrees C. So if you'd covered your eyes and you simply open it up and realize that I raised the temperature of the water to 80 degrees C, you could not tell me which way I had done it. You could not tell me if I'd done it by heating it or if I'd done it by work. Another way of looking at it is this. You pull a cup of water from the ocean. You cannot tell how those molecules got into the ocean. They could have came by rain. They could have come down by a river. You cannot say. All you know is that they're in the ocean now. And so it is. Once the energy gets into the system, becomes internal energy, how it got there, whether by work or heat or whatever, is completely lost. We do not know. Those are transfer processes. Energy is what is fundamental, and internal energy is what is defined for state. So it's not correct to say that a system has heat or a system has work. It can't. That's the transfer of energy to the system. What the system has is internal energy. Now, in those days before people understood this idea, they had defined something called the calorie, based again on this idea of this fluid. It was the energy required to raise 1 gram of water 1 degree Celsius. We now know that we really should have used energy units, the joule. 1 calorie is equal to 4.186 joules. 1,000 calories is the amount required to raise 1 kilogram of water 1 degree Celsius, or equivalently 1 Kelvin. That would be 4,186 joules. That's also in diets and things called the dietary calorie. So when people say I'm going to eat 500 calories, they really mean 500,000 calories. The calories they use are the diet calories with the big C, not CAL, the abbreviation usually small c, cal, or just small c, which means this calorie. They use the dietary calorie, which is in thousands of joules. So these may be useful if somebody gives you heat transfer in calories. You'll need to convert it over to joules. Now, we just saw that it said for 1 gram. We know that the internal energy is dependent on the number of atoms inside the system. So it takes more energy to raise the system of a whole bunch of atoms by a certain temperature than just a few. The temperature tells you how much you raise on average 1 molecule. So Let's figure out how to relate the amount of heat you need to add, for instance, a particular mass of a substance to raise its temperature. This leads to the concept of specific heat. Consider a system with an internal energy U sub I. Now, by kinetic theory, we know the internal energy is related to the number of atoms to the internal energy per molecule. And this is equal to some constant. Now, we a minute ago had this constant as 3/2, but some constant. Maybe it's not going to be 3/2 for a solid, times the number of molecules times the temperature initially. So A times initial temperature relates the energy per molecule to the temperature. So measuring the temperature is proportional to the internal energy per molecule, and N gives us the number of atoms or number of molecules that we have in the system. If we now give Q units of heat to the system, we raise the internal energy, U sub F, by Q plus whatever it initially had. But this has to also be equal to A times N times the final temperature. Now, that means that we can subtract the final internal energy, that is how much energy the system has at the end, from how much it had initially. If we do that, delta U, we get Q plus UI minus UI. That's just the amount of energy we added as heat. And over here, we get A times N times TF minus TI, which is some constant times the number of atoms times the change in the temperature. So what we find is that as you heat a substance, you raise its temperature. If you put twice as much heat, you'll cause twice the change in temperature of the object. So we could plot Q here, and we could plot delta T, and we see that we have a straight line, but the slope of that line depends on this constant times how many atoms you have. Now, the number of atoms is directly related to the mass of the system, and it's also related to the number of moles of the system. So we could rewrite this a couple of different ways. We could write Q is equal to some constant times N over Avogadro's number times N sub A delta T. And we could group the constant and Avogadro's number together to make a new constant. That's just a constant. But the number of atoms divided by Avogadro's number is the number of moles. Or we could choose instead to write Q in terms of this number times the number of atoms divided by Avogadro's number times the gram molecular weight. And on the other side, we could again cancel all that out. Times delta T. This again can be rewritten. This is the number of moles times the gram molecular weight. That's going to be equal to the mass. So we have A times Avogadro's number over the gram molecular weight times the mass times delta T. And again, this is just some constant. So as we raise the amount of mass, if we double the mass, it'll take twice as much heat because we doubled the number of atoms, and therefore we doubled the amount of internal energy that was required. Now, these are usually written in a little simpler forms in which we just write this constant as a single value. And that value, when written like this, is called the specific heat. So the result is generally written as follows. The amount of heat that you need to add Q is equal to some value times the mass times delta T. And if this is done with a gas, you have to be careful to explain what process this was done. Was this done under constant volume or constant pressure? C is a specific heat. It's the heat required to raise 1 gram of the substance 1 degree in temperature. You can also write it in terms of the number of moles, in which case this is little c times N times delta T. And this little c is called the molar specific heat. And it's the amount of energy or heat required to raise 1 mole of the substance 1 degree. People usually like to compare apples to apples, so they compare moles to moles, because 1 mole of a substance has the same number of atoms, but 1 gram of a substance does not have the same number of atoms. So while this is useful often for calculating things, where you have a bar of a given mass, this is far more useful from a physicist standpoint in understanding what's going on between heat and change in temperature, at least in the days when this was a hot field of study. In fact, in the 19th century, at the end of it, in the early 20th, studying how specific heats change for different types of material was a way to study the energy and the inner workings of the atomic world. And so it was a hot topic at the time of Einstein's PhD thesis. Now, in the next one, we'll go and show how we can find the specific heat of an ideal gas and how that's related to the nature of the forces, which is what physicists want to do. They want to measure something macroscopically so they can look in and determine what's going on in the microscopic world that they cannot see. We'll talk about that in the next video.